Hello everyone. In this video, we are going to look at creating path in CoppeliaSim. And I have two demos for you. The first one is to generate a path like this via code. And the other one is to create it manually by basically moving the control points like this one. And then I show you how to make a mobile robot like this, move along the path, and then you can also plot the XY position of the dummy that is attached to the robot, as I showed you in my previous video. So you learn several important things. So let's get started. So first one is how to generate it with a code. Okay, so if you want to do it with a code, all you need is a simple script that you can attach to the scene as a child. And let me talk about this code for you. Now it's a little bit long, but a lot of it is really indexing. So first you bring in the sim. These are the variables that you can control, including, so here what I want is a circular path. So the radius is there, the number of control points along it is there, whether it's closed or not, that's a Boolean operator. There are subdivisions, there is a smoothness, there is extrusion height, and so on and so forth. So these are the parameters. This is the inner radius of it, from center to side of the basically original hexagon. And why do I call it the hexagon? I'll explain it to you. So this is what you have in the beginning. Okay, these are the parameters you can tune. Then at each point, each control point on a path in CoppeliaSim, the data for it should be given as 7 data points. The first 3, because this is the pose at that point, the first 3 are x, y, z for the control point, and the other 4 numbers are the quaternion. So the orientation here is given by quaternion, not by Euler angle. So I start these control points as empty, and then I use a for loop, which goes from 0 to number of points minus 1, so 35. And then basically here, what I'm doing is I calculate the position x and y of the points using the radius times cosine of an angle and sine of an angle. And you see the angle is something that depends on the loop counter I. And so basically if you have like 36 points, each time this angle is going to be like for I equal 0, it's going to be 0. For I equal 1, it's going to be 2 pi over 36, then pi over 36, then 2 pi over 36, and so on and so forth. And then cosine and sine of that multiplied by the radius will give you the x and y of the control point, as you can see. And then the z of it is 0 because I want them all to be on the floor. And then for the quaternion here, I'm using 0, 0, 0, 1. Okay, which basically means no rotation and unit quaternion. Okay, so these are a bunch of XY points on a circle, 36 of them. These are my control points. Good. Now, once I create these, it is time to pass them to Coppelia to create the path between them and to extrude it. If you want it extruded, you don't have to make it extruded. So the first thing I do here, so the command I'm going to use is this command here, sim create path. And this command needs the control points that you already made. It needs the creation option. Here I use 2 plus 4. 2 is used if the path is closed, and 4 is used for extrusion or auto shape enabled. So when I use 2 plus 4, it basically makes sure it's closed and it also extrudes it. And here I'm just making sure the path is closed because that's what I want, because you can create open path as well. I'm going to show you in the next demo of this video. And then this is the direction for the extrusion. You see the direction is 0, 0, 1, which means in the z direction I want to extrude how much? As much as this height here. And then here I create the path handle using this command. As I said, I pass to the control points, the options. I tell it how many subdivisions, what is the smoothness. I give it this option here, 0, and then the direction of extrusion. And if you ask what is that 0, let me explain that to you. So this parameter here is called the orientation mode. And if I want to add that somewhere for you, so let's say after this parameter, I can go ahead and add another local parameter, call it the orientation mode, and use 0 here. Okay, and then when I get to here, instead of 0, I use orientation mode. And here, basically, if I want to add explanations, 0 equals basically no correction. And correction comes from, by no correction means use those quaternion values that you already gave it, all of these zeros and ones. Okay, but if you give it 1 means basically automatic correction using tangent directions. And then we have 2 and 3 and 4, 2 and 3, and 2 means follow the up vector, the reference. 3 means use the Frenet frames and so on, which is basically what we call tangential normal by normal. So there are several corrections that you can do. So here we're going to use 0, and so we create the path handle. And this is a check that if it didn't if the path is not created, create an error message. And if you want, we can just get rid of it. Then the next thing we need to do is to basically create the cross section of the extrusion. Here, the cross section we want is a hexagon cross section. And so we need to use this radius of the hexagon cross section that we already had. And then here we say we want 6 sides, and then we provide the sections for it. Okay, so these are the 6 sections of the hexagon created. And here we make sure that the hexagon is closed. If it's not closed, then you will have an error. And finally, there was another section that I decided to get rid of it because that was using a separate command for creating path, and I'm not using that here. So if you go and look at the user manual for path in CoppeliaSim, the command that it uses is this guy here, generate shape from path. And this command, unfortunately, does not have help. So if you go here and look, it does not have any help. And when you try to work with it, typically it picks on you on this variable section. And I tried to use it several times, so it gave me error. So I decided to skip that altogether and go with this command here, which is basically doing what I want. So now this simple code here should do the job for us. So let's go ahead and run it again. Okay, so let me stop it, run it again. And you can clearly see that the path is generated, and it has 30 from 0 to 35, 36 basically control points. And it added this shape, which is the hexagon here for the extrusion. Okay, so this is creating a path using code directly. And here, these are warnings, these are not errors. It says you use the matrix implicitly, go ahead and directly bring it, or use the newer command sim eigen that does the same thing. But since it is working, I'm okay with this code, and I don't want to update it with the new code. So let's just keep it as is, and I'm gonna share this script with you on the video description so you can use it. Now, if I go to the part that I manually created and then move the control points, which is more time consuming, of course, but the good thing is it stays here, and then I wrote a code for this robot to follow the path. So let me show you that second method here. So in this method, you just simply right click and say add a path, and you can have it open or close. So let's say I make a closed path like that. Let me just grab it and bring it somewhere else like that. And now if you look at it, this path here is created with 16 points. The last point and the first one are on the top of each other. Not really, actually, they are not on the top of each other. There is a small gap between them. But if you zoom in, let me zoom into it so you can see that it has all of these control points. There we go. So you see all of these small circles. These are your control points, or the dummies here. And I can literally move them anywhere that I want. And this script here that I have, this one, basically in this case, this is just like a sample thing. It doesn't really generate this, because if I use this one, this section basically is a square. Okay, so here this is a square, and I'm not using that, but these control points is what I can really control here. So let me show you. For instance, I click on this first control point here, and then I grab it, and then I put it wherever I want. There we go, right? And then I click on the second control point, and I can move it wherever I want, or I can position it using this wherever I want. So here you can manually basically define your path here. So you see already it is changing, and you see these are just the control points. The way that the curve is created is using what we call the Bezier curve. If you don't know what Bezier curve is, I recommend you watch my channel. I have a video for Bezier curve, and you can see with more detail what is a Bezier curve, and this is how these curves are made. Okay, so you just click on whatever control point that you want to modify, and then put it wherever you want manually or by typing the position. Okay, there we go. So here, let's say this is my curve. Now, if I want to extrude it like this one, what I can do is double click on this icon right next to the path or to the script, especially path here, and you can say, hey, generate an extruded shape. And there we go. Here is an extruded shape, right? Very easy, okay? So I can easily go ahead and do that. And as soon as I do that, it adds this shape for me now. And I can double click on this shape if I want. And let's say I want to change the color. I can go ahead and change the color, right? So I can do whatever I want with the color. There we go. And I can change the shininess or anything of it. There are some other parameters that I can change about the texture, the geometry, and so on. Okay, so you see I can apply changes and so on, and let's say this is my new path, and now I can make the robot go through that path. So this is manual creation of that. Now, what is the code that I used here to force this robot, this mobile robot, follow the path? So to explain that for you here, I created this path, this purple path, and I added a dummy to the robot, and I connected the graph to the robot, to the dummy, using this code that I showed you in my previous video. So this part of it is very similar. The only thing you have different here is the control of the robot itself. So instead of robot just going around the circle like last video, here I changed the script of the robot, and you can see here that the code is different. So here I get the handle of the path, get the handle of the robot. Then I need to get the data of the path. Remember, the data of the path comes like this. It's a big matrix. Each row of that has X, Y, Z for any control point, and the quaternion for that control point. So it has 7 columns. So once I get my data of the path and convert it to a double table, unpack it, then I go ahead and first thing is I divide the size of this path data by 7 to give me the number of rows or the number of control points. And once I have that, now I can go ahead and read the first 3 data points of each row, which is XYZ of it, and store it as the path position. So these are the XYZs of the control points. And then I read the data from 4 to 7 of the rows each, and I call them the path quaternion, the QXY and QZ and QW of each control point. Now that I separated these 2 data points, I can use them to basically control the robot. But how? First thing is, I need to basically create the cumulative distances along the path and the total length of the path. So for that, I pass my path positions XYZ, and I say they have 3 dimensions XYZ. And this command get path length, give me 2 outputs. One is the total length of the path. The other one is the path length cumulative. So at the first control point, this is 0. At the next control point, that's the Euclidean distance between point 1 and point 0. And then at point 2, that's the Euclidean distance between point 0 and 1, plus the Euclidean distance between 1 and 2, and so on and so forth. It's a cumulative distance. Why do I need that? I'll tell you in a second. I set up my linear velocity along the path. This path position, if I use 0, that means start at control point 0 all the time. So you can start it at any control point when you start the code. Here I want to start it always at control point 0. I also need to get my simulation time before I run the control code, and I use this command set stepping true. What is this one? So when you set it to true, it enables stepping mode for threaded script. And in this case, I did use a threaded case script to run it faster, or on several threads basically. So now look, this is my control algorithm. I said as long as the simulation time has not run out, go ahead and do, right? So it keeps doing it until the simulation stops. While not that, do what? Get the new time and then compare it with the previous time to see how much time has spent. Multiply it by the velocity to give you the displacement. Add it to the position that you have along the path and call it the new position along the path. Remember, you are starting at basically point 0, and then with this velocity and the time spent, you get your new position along the path. Now that you know the path positions, which are the locations of XYZ of the control points, you know the cumulative distances along the path, and you know your actual position along the path, which is really a travel distance. Now you use this interpolation method, get path interpolated configuration, to give you exactly the position and orientation of the robot at a travel distance. Okay? Because you want to know what is the position and what is the orientation of the robot at any arbitrary point along the path. Let me explain that. So look, these green ones are your control points, and let's say this is the point 0. So if I'm right now here between this control point 2 and 3, so my travel distance, when I compare it against the accumulated distances, it tells me I'm here. I'm, let's say, between point 2 and point 3, okay? So I know I'm there, but do I know my position and orientation at that point? No, I only know my position and orientation at these 2 neighboring points. I don't know it over there. So that is what you are doing with this interpolation, to find your position and orientation at the intermediate points, at points between the control points. That is what you do with this pose. And then you will use that pose basically to set the object position, okay? But we also use that pose for something else too. What do we do? So not only we need to make sure the robot is following the path, we need to make sure the orientation of the robot body matches the orientation of the tangent to the path. For that, we're gonna go and look a little bit ahead of us on the path, okay? And this is the small distance ahead of us along the path, this epsilon. You can make it bigger or smaller depending on how much you want to move forward, and look. And then look what we do. Here, we again use the path positions, the critical points, the control points, the cumulative distances, but instead of my location, I use my location plus a little bit. So now I get my basically pose of the robot a little bit ahead of me, like a few centimeters, a few millimeters ahead of me. And then what? This pose has 7 numbers, if you remember, X, Y, Z, and the 4 quaternions. So I subtract the X's and the Y's, which are the elements 1 and 2 of the pose, ahead pose and the current pose, and I get my dx and dy between my point, my current point, and the next point. And then using this dx and dy and the arctangent function, I calculate what? I calculate the direction of the tangent, the angle of the tangent, which is the yaw angle of the path at the current location. So I'm doing a numerical derivative basically here. I'm finding dy and dx. I take arctangent of that to get my yaw angle or tangent angle, okay? And then if that tangent is very tiny, I can use the Euler angle and get my yaw angle. Once I get my yaw angle, then I convert it to the required quaternion to command the robot. Okay, because in order to command the robot, you have to give it position and quaternion. You cannot give it position and yaw angle. So here you convert your yaw into a quaternion, and now that you have your position and now that you have your quaternion, you set the object position and quaternion to those numbers, and you have to say these position and orientation are with respect to which frame. -1 tells you is with respect to the word frame, not with respect to any other frame. So once you set the position and orientation of the robot to the new pose and quat, and you update your time, then you advance the simulation one step ahead, and this is basically all you need to do. So it looks a little bit heavy, but if you go through it and pay attention to the explanations I did, this should exactly tell you what you're doing. And let me run this code for you so you can exactly see what it is doing right now. So you can exactly see that the XY graph shows you the kind of curve that the robot is passing, and it is beautifully passing through all of those. Right, that's the closed path, and you can look at the time graph of X and Y as well. So hopefully this video was useful to you. I will share both of these scripts for the robot and the one that creates the path by code with you under video description. Feel free to take a look at them and learn from them. Thank you so much for your attention. I'll see you in the next video.